welcome to Duodecimal Division. My name's Eric Larson, and this is the fifth video in a series of videos that I'm calling The Secrets of the Numerals. So what we're doing is looking at this geometric pattern, and I'm showing you how somebody used this pattern to come up with the various symbols that represent the various numbers. So we're going to go to the fifth circle in the series, but I don't have it drawn here. What I'm going to do is actually just show you if we're just using this pattern to generate our grid on blank paper or a blank surface, what I would have to do is now work out how to build the diagram some more. So right now the compass that I have is set, there it is, it's set to the length of 2. 1, 2, we just say drew that circle. What I would do now is move my center point to this point here and adjust my compass so that it has the length from this point here to that point there. So you see we're going over 2 and up 1. So applying Pythagoras' theorem, 2 squared is 4, plus 1 squared is 1, 4 plus 1 is 5. So this length here is the square root of 5. And once I've set my compass, I would put it back on this point here and draw another circle. And then as it went up, it will be crossing these points, which I've already created using this diagram, and then we'll be able to draw the next sort of series of squares on the Cartesian plane, and we would have the next circle in the series. So I'm going to switch my board up so we have a smaller version of this so I can fit everything on, and then we'll look at the numeral that represents the number 5. Okay, so here we are. A smaller version of the same diagram, more circles. So we're going to go to the 5th circle in the series. 1, 2, 3, 4, 5, and you can see I've already put points on all the spots where that circle is crossing the lattice points or crossing the grid on lattice points. So again, lattice points, you can see all the points where the horizontal and vertical lines are crossing each other. And this particular pattern has 8 lattice points, or the square root of 5 radius circle is touching down on the Cartesian plane on 8 lattice points. So there they are. And so what I'm going to do again is go off of one of those lattice points and draw some lines. And we're going to go off of this point here, which is consistent with if you think about the design of the 5, we know that the line that comes off of it to define the angle isn't coming right out of the top, and it's not coming off of the side, but sort of somewhere in between. So we're going to go to this point, and I'm going to draw a line going up the length of 2, 1, 2. And then I'm going to draw a line going along the top here, the length of 3. 1, 2, 3. Just like that. So there, right away, again, I'll write that down, 3 and 2. So 3 plus 2 is 5. So right away we have a combination of lines here that result in the length or the value of the number that this symbol is representing. So now I'm just going to trace a portion of the circle. We're going to start at that same lattice point and just follow it around like this. We're going to go to this point right there. Okay, so we're stopping at that point, again, another lattice point. So very well placed symbol on the grid, all on lattice points. We're encompassing those ones. We've just missed these two here. So that's basically it as far as the symbol itself. That's why the numeral for the 5 looks the way that it does. And for this symbol, we've incorporated the right angle. We're kind of working our way through. For the 2, we had the 45-degree angle. For the 4, we had the 30-degree angle. For the 5, we've got the right angle. And as far as lengths go, we've got the length of 5. I'll just write it, I think, yeah, here's no problem. We've got the 5. And this actually here, between that point and that point, is the length of 4 between those 2 points. So I'll put that down there. And of course, the 3 and the 2. 5, 4, 3, and 2. And there's also something interesting. If you could draw a line from this point here, going up kind of through the center to this point here, and then to this point here. So this is a line similar to the square root of 2 that had the symbol for the 2 had the square root of 2 line inside of it. This one's sort of implied, but a line that's been broken down, or you could break it down into units of square root of 5. So I'll just put square root of 5 here also. So that's basically it as far as sort of hidden geometric information, I suppose. I could draw, again, a straight line going down through those 2 points to this point here and over to this point here. And we have a triangle again with the dimensions, same proportions as, you know, over 1 and up 2. Here it's 3 and 6. Again, built into that same pattern, the same design. It's interesting how they chose the 90-degree angle here. Now, as the circles are getting larger, we can see that we have the potential of connecting the points inside the circle and creating lots, like basically rectangles, you know. So the right angle there is inside, it's able to encompass inside the circle as far as, you know, qualities of the square root of 5 and how it fits on the Cartesian plane, that sort of thing. So that's why the numeral for the number 5 looks the way that it does. I'll put the board behind so we can see more clearly. So actually, I'll just for fun, I'll write down, we got this distance here, which is 2 root 5. So again, to give you the base 12 equivalence. So there's no real base 12ness to this particular symbol, but the distance from there to there is 3 root 5. So see if I can figure this out in my head. So 2 squared is 4 times 5. Normally that would be 20. And base 12, that would be the square root of 18. Right, one group of 12 plus 8, and 3 root 5, the distance from this point here to there, 3 squared is 9 times 5, in base 12, that works out to the square root of 39. 3 groups of 12 again plus 9, 36, 46, 45 would be normally. So a little bit of extra information there. Keep remind you that we're doing this in base 12. I think that's it. So there you go. I hope you enjoyed that presentation. And now we're going to go to the next circle in the series, the circle with the radius of the square root of 6. And we're going to see why the numeral that represents the number 6 has the distinctive shape that it does. And this one is going to be back to a very specific base 12 numeral, and that you have to be aware that we're doing it in base 12. There's going to be some base 12 math in there also. So I hope you can join me for that. Thanks for watching.